Hello, I will be solving a modified problem from thermofluids.net along with a what-if study. We will analyze a Brayton cycle using air as a working fluid. In this problem, the air enters the turbine at 1 megapascal and 1000 Kelvin and leaves at 125 kilopascal, 610 Kelvin. Heat is rejected to the surroundings at a rate of 7,000 kilowatt and the airflow rate, m dot, is 25 kilograms a second. The compressor has an efficiency of 90%, and we're first asked to determine the net power output. In the interest of time, I've already entered the given information into TestCalc to verify our solution. However, there are still a few pieces of information we need. That information will be explored in the next few slides before we take a look at TestCalc. The information we still need is T1, the compressor inlet temperature, T2, the ideal compressor outlet temperature, and T3, the actual compressor outlet temperature. We can determine the compressor inlet temperature, T1, by using the information we are given regarding the heat rejection rate. Since we are also given the temperature at which the air exits the turbine, T5, we can easily determine T1. T2 is the temperature that air would exit an isentropic compressor. This represents an ideal case. We know that the change in entropy is zero, as this is an isentropic process. Because we know the inlet and outlet pressure, and we have already solved for T1 in the previous slide, we can determine the outlet temperature, T2. T3 is the actual temperature of the air that exits the compressor. T3 varies from T2, because in reality, the fluid does not undergo a perfectly isentropic process in the compressor. Because we are given the compressor efficiency, and we have solved for T1 and T2 in the previous slides, we are able to determine T3. The ideal work for the compressor is a work associated with T2, because that represents an isentropic process. We are now in TestCalc. I want to begin by showing you the TS diagram for this Brayton cycle. Note that point 3 is greater in temperature and entropy than point 2. This is because point 2 represents the perfectly isentropic compressor and point 3 represents the outlet for the actual compressor outlet. I will now run through the different states in the cycle and explain the variables as I've entered them into TestCalc. We will begin with state 1. P1, the compressor inlet pressure, is equal to P5, the turbine exit pressure. T1 is the same as what we have solved for in the PowerPoint slide, and m.1 was given in the problem statement as 25 kilograms a second. I would like to note that m dot is the same for every state in the cycle. State 2 is the outlet of the compressor, assuming an isentropic process. The pressure at state 2 is the same as the inlet pressure of the turbine, P4. T2 is the same as we have solved previously. State 3 is the actual outlet of the compressor. The pressure is again equal to the pressure at state 4. T3 is the same as we have solved in the PowerPoint, considering the efficiency of 90% for the compressor. State 4 is a turbine inlet, and the pressure was given as 1 megapascal or 1000 kilopascal. The temperature was also given as 1000 Kelvin. State 5 is the turbine exit, and the pressure was given in the problem statement as 125 kilopascal, and the temperature was given as 610 Kelvin. In the I/O panel, I have defined Q out as 7,000 kilowatts. In order to determine the compressor work, I defined the inlet of device 1 as state 1 and the outlet as state 3. As shown, TestCalc was able to solve for the compressor work. Note that the work is negative. Considering WinHIP, this means that the work must be put into the system at the compressor. In order to determine the turbine work, I defined the inlet of device 2 as state 4 and the outlet as state 5. Note that the turbine work is positive, which means that the useful work is exiting the system. Also in the I/O panel, I've defined the net power output, WNet, to be turbine work minus compressor work. This generates the final answer to the problem statement. In this case, the net power output is 2,288 kilowatts. Now we have the what-if scenario left. We are asked to determine the net power output if the compressor efficiency is decreased to 70% and the heat rejection rate is increased to 8,000 kilowatts. To make the appropriate changes in TestCalc, I will enter state 3 and change the efficiency from 90% to 70%. Additionally, I will enter the I/O panel and change the value of Q out from 7,000 to 8,000. We will then allow TestCalc to calculate the new net work. As shown, the new net power output in the what-if scenario is 1307 kilowatts. The net work has decreased dramatically, almost by half. This what-if scenario can give us insight as to how much of an impact both the heat rejected and the compressor efficiency can have on the overall cycle.